Welcome. I'd like to welcome everybody to our 2025 Dr. Bruce J. Nelson Class of 74 Distinguished Speaker Series. I'm Dan Tamayo. I'm an assistant professor here in the physics department. This year's series, Doing the Impossible, Journeys Across Space and Time, highlights innovation at the intersection of STEM, space, and human possibility. We began our series in September with astronaut Jose Hernandez, as he shared his journey from being the son of migrant farm workers to space shuttle mission specialist. Tonight, we're lucky enough to welcome Nobel Laureate Kip Thorne, who will reveal the decades-long effort to detect gravitational waves from colliding black holes, exotic objects that he also helped bring alive in the movie Interstellar. Before I introduce our speaker, I'd like to acknowledge the generosity of the family of the late Bruce J. Nelson, Class of 74, for establishing this educational series to honor Bruce's memory. Bruce died unexpectedly in 1999, though not before having a tremendous impact on the many people whose lives he touched. As an unconventional, eclectic, and irrepressible free spirit, he graduated from Harvey as an independent program of studies major, and later earned his master's in computer science from Stanford and his PhD in computer science from Carnegie Mellon. At the time of his death, he was the chief science officer at Cisco Systems. We are honored and grateful to the Nelson family for the opportunity we have each fall to host exceptional speakers who are at the forefront of their respective fields. Okay, so now it's my pleasure to welcome our guest speaker. Again, our series is called Doing the Impossible. I think Kip will convince you over the next hour that they were able to do almost exactly that. Right, for that feat of detecting these gravitational waves that pass through the Earth, Kip and his collaborators have won a longer list of prizes than I could possibly list, but including the Nobel Prize in Physics in 2017. Remarkably, in addition to doing all this science, Kip is an incredible science communicator. And this is close to my heart because before going to grad school, I got his book, Black Holes and Time Warps. And this was one of the big inspirations that led me to study astrophysics in grad school. He signed it for me today. When I was at Cornell, a lot of my best friends were on the 6th floor working in the numerical relativity group that was simulating colliding black holes in collaboration with Kip. And the year after I graduated was the detection of the first gravitational waves and was such an exciting event. So I think it's really rare to meet somebody who is absolutely, obviously at the top of their field in science, who is also such a powerful communicator and an ambassador for science, for everybody around him. So please join me in welcoming Professor Kip Thorne. We'll let him take it away.
Thank you very much, Dan. Can you hear me? Okay, let me get oriented here. And can you see my cursor there? Yes, good. This talk is going to be a little bit different from what many of you had expected. I won't talk about Interstellar. I will talk about black holes, but I won't talk about Interstellar. I also am what I'm really going to focus on is the following, that the quest to create gravitational wave astronomy was a quest that took approximately 50 years of my life and of Ray Weiss's life, my colleague at MIT who worked on this so closely with me. It, in the end, took $1 billion of taxpayer money, yours. It took 1,000 people in 16 nations, 81 different institutions, all working closely together on what was probably the most technically difficult thing that physicists have ever done, the highest risk, one of the highest potential payoff projects and I'd like to tell you how we did it. And I'm not going to tell you the technical details of how we did it. That's for a different audience on a different set of 1,000 days, if they really want to understand the full technical details. But I am going to tell you what I think were the essential points along the way. And so this is going to be historical, and it is based on the fact that at the beginning of the pandemic, I saw that my colleagues who had been leaders in making this happen, that they were going to have some time on their hands because the lab was being shut down. And so this was an ideal point to pull them together and to start writing this technical history. And so it's a collaborative effort of 6 of us with consultation with over 100 of our colleagues. Well, you're going to get out of this the essence of what I think were the most important points along the way. Okay, so let me go forward. This is going to be in the form of a set of vignettes or little snapshots along the way, just to pick up the essential points. The first one is 1962 to 65. I'm a graduate student at Princeton University. I've gone there specifically because I am in love with general relativity, Einstein's theory that describes the warping of space and time. And John Wheeler there is the guru of relativity of that era. So I go there to learn relativity from John. And from him I learn that there is very likely what I today will call the warped side of our universe, objects and phenomena that are made entirely or largely from warped space and time. The examples that I'll be talking about today are black holes, neutron stars, which are partly made from matter and partly from warped space-time, the Big Bang birth of our universe, and gravitational waves. For example, a black hole that I'm showing you here, in our universe it looks like just a black sphere, sort of like a bowling ball. But its circumference is much smaller than its diameter. You might ask, how could that be? And a simple analogy can explain that. Let's take a child's trampoline, a sheet of rubber, and put it up on tall stilts that I'm not showing here. And let's pretend that you're an ant, you're a blind ant, but you have been studying at Harvey Mudd, and so you really know your stuff. And so you go marching around here measuring the circumference around this region, and then you go marching down there to measure the diameter. And my gosh, the diameter is enormous compared to the circumference because your whole universe is this sheet of rubber. And you say to yourself, well, obviously I live in a warped universe. The space in my universe is warped. And this is precisely the same diagram as I need to talk about black holes. If I take a black hole, I take an equatorial slice through it, so I then have a two-dimensional surface. I'll only look at that two-dimensional surface. That surface we can think of as warped in a higher dimensional space. In the movie Interstellar, that's called the fifth dimension, or the bulk. Physicists sometimes call it the bulk. And so here is the bulk that we're looking at. And it's the same diagram. That equatorial slice of the black hole is warped in the bulk. Here where we did have a rock, there's a singularity, a region where space and time are so highly warped that Einstein's general relativity fails. But what it looks like from the bulk is a funnel. So I'll just refer to that as a funnel in the bulk. It's what a black hole looks like as seen from a higher dimension. Now, if I go falling into this black hole trying to send you signals with a little microwave antenna, there's a surface called the event horizon, or just the horizon. If I fall below that horizon, then the signals and I get pulled inexorably toward the singularity, and there's no way for me to get the signals back out through the horizon to you. I'm lost. My signals are lost from our universe. That's a familiar aspect of this. Now, in addition to the warping of space, there's a warping of time. If I go down and I hover just above the horizon, time, as measured by me, slows down enormously compared to time back on Earth. For the planet that is in orbit around the Miller's planet in the movie Interstellar, that's in orbit around the black hole Gargantua, 1 hour on Miller's planet is 7 years back on Earth, you may remember. So enormous slowing of time. Right at the horizon, time slows to a halt, and beneath the horizon, time flows in a direction you would have thought was a spatial direction, downward toward the singularity, which is why nothing can get back out. Another reason, nothing can move backward against the forward local flow of time. If things can go backward in time, they have to do it by going out in the universe and coming back before they started. They can't go against the local flow of time. That's a fundamental law of physics. In addition, the black hole spins on its axis and it drags space into a whirling motion, so fast whirling motion near the horizon and much slower farther away. And that whirl of space, this warping of time, the warping of space, they make up the warping of space-time of a black hole. This is what the warping looks like if I make a precise diagram of this is the actual shape in the case of a rapidly spinning black hole. Where it is yellow, that's where time is flowing at 10% of the rate that it is far back away. And where it's black, that's the horizon, which looks like a circle here, but when I restore that missing third dimension, that circle becomes a flattened sphere. And then the white arrows are the angular velocity of the dragging of space into whirling motion around the black hole, and fast near the horizon, slow farther away. What warps the black hole space and time? The energy contained in the warping. The black hole is held together by what we call nonlinear self-interaction. It's what is sometimes called a gravitational soliton. Now, there's a much greater richness to the warping of space-time around a black hole, and I'm saying this all to give you some sense of the enormous richness of warped space-time. There's something else here that we have not often talked about. Leah Halloran, my partner in this book, The Warped Side of the Universe, her paintings and my poetry, she does a painting of her wife, Felicia, just above the horizon of the black hole. Felicia looks down, and her head is feet are closer to the black hole than her head, and so her feet are whirling around faster than her head, and that means that her head sees her feet going around counterclockwise. If you think about it, that means her feet will see her head going around counterclockwise. It's like taking a wet towel. You wring water out of a wet towel. If your left hand sees your right hand going counterclockwise, then your right hand will see your left hand going counterclockwise. So there's a counterclockwise twist of space. I call this a counterclockwise vortex of twisting space sticking out of the north pole of the black hole, a clockwise vortex of twisting space sticking out of the south pole of the black hole. In addition, down inside the black hole there are singularities. There are actually three of them. I'll just talk about one, a chaotic singularity, which is oscillating in a wild, chaotic manner, but at one particular moment of time, the singularity has sticking out of it a tendex. A tendex is from the Latin tendere, to pull, in the same way as vortex is from the Latin vortere, to turn. So there's a tendex sticking out of the black hole that stretches Leah's wife out along those blue tendex lines, and red tendex lines that squeeze her from the side, so she is, the technical word is spaghettified as she goes in there. But then that spaghettification oscillates in a wild, chaotic fashion. It's a very lethal, chaotic fashion. You don't want to go in there, and in the movie Interstellar, they carefully avoid this chaotic singularity. Well, I'm going to stop at that point, and I'm going to then summarize for you what is a black hole. And this is going to be taken from my book with Leah Halloran, but it's a animated version of her paintings, and it's me reciting some of the poetry. And we begin with us explaining what is Felicia's wife, or Leah's wife, Felicia. What is Felicia? She's the sum of all her parts. Her face, her silken hair, her arms and breasts, her hands and legs and feet, her heart, her brain, her precious personality. And what is a black hole? It's the sum of all its parts. It's space that is warped, the funnel of bulk being seas, its vortices of whirling space, its tendencies that stretch and squeeze, its slowing time and down cascading time, its horizon and its singularities, all made from warped space-time. So this gives you some sense of the enormous richness and variety of phenomena you can get just made from warped space-time, not made from matter like you and I. It was 1 year after he formulated general relativity that Albert Einstein used it to predict the existence of gravitational waves. And so here I'm going to describe what a gravitational wave is. We have a gravitational wave propagating into the screen, and what it does is it stretches and squeezes space orthogonal to the propagation direction, so in the plane of the screen. I have a set of free particles in a rectangular array, and they're just floating out in space, and each of them behaves inertially. It just moves under the effects of its own inertia. And when the gravitational wave comes along, there are two Tendex lines horizontally that stretch and vertically that squeeze, and then those stretch and squeeze oscillates in time. And so as a result, the particles move with respect to each other in this oscillating way as each of them behaves inertially. And so if you want to detect gravitational waves, you want some way to monitor a oscillating stretch and squeeze that are opposite along perpendicular directions. And so that's the key to it. So my second vignette, 1972, I have moved to Caltech. I have built a research group at Caltech of young people who are working on issues related to the warp side of our universe. And together with Bill Press, a student of mine, and in consultation with a number of colleagues and other students, I am developing a vision for gravitational wave astronomy. And part of this is that there really are only two types of waves that can be created very far away and travel to Earth, bringing us information about the universe out there, as according to our understanding of the laws of physics, gravitational waves and electromagnetic waves. And it was, and the properties of the electromagnetic waves, the electromagnetic waves can include light, radio waves, X-rays, and gamma rays. And it was Galileo 400 years ago who he built a little optical telescope, pointed it at Jupiter, and discovered Jupiter's 4 largest moons. And in the process, he initiated instrument-based electromagnetic astronomy. And so part of our vision was to do for gravitational waves what Galileo did, to create gravitational wave astronomy in the same manner as he did electromagnetic astronomy. And because gravitational waves are made from the same thing as black holes, from warped space-time, they are the ideal tool for exploring the warped side of our universe. And that is a key point for the whole story that I'm going to be telling you about today. There is a huge amount of information can be carried by gravitational waves. They're carried in what we call the waveform. These are like the waveforms you see for sound waves on an oscilloscope. This is a gravitational waveform that I'm showing you here. It's a pattern of stretching up and squeezing down as a function of time, and it carries information just like a symphony's sound carries information by tickling your eardrum as a sound wave comes into your head. Now, electromagnetic waves I'm going to contrast with gravitational waves side by side. Electromagnetic waves are oscillations of the electric and magnetic fields that travel through space-time, while gravitational waves are oscillations with the very fabric of space-time itself. Very different. Electromagnetic waves are emitted by electrically charged particles when they oscillate. Gravitational waves are emitted by the motions, oscillations of massing bodies, such as stars, or by the dynamical oscillations of warped space-time itself. Electromagnetic waves are very easily absorbed, all too easily absorbed and scattered between us and their source. Gravitational waves are exceedingly penetrating. They're never significantly absorbed or scattered. Even if they were emitted in the Big Bang, they still travel to us without any significant absorption or scattering. And so if you think about that for a little while, some implications become pretty clear. First of all, many gravitational wave sources are not going to be seen electromagnetically at all. You're going to be seeing things where the electromagnetic waves, if there were any at all accompanying them, they haven't gotten through the universe to us. And huge surprises are likely as we get into gravitational wave astronomy. It was in that same year, 1972, as we were beginning to develop this vision, that Ray Weiss, my dear friend, we had been together at Princeton when I was a graduate student, he was a postdoc. He sent to me and to other colleagues a technical paper in which he described a new type of possible gravitational wave detector called a gravitational interferometer with delay line arms. Now let me make sense of what those words mean, parse those words. We have 4 mirrors hanging from overhead supports, 2 along this arm and 2 along that arm. In the end, we're going to be talking about 4 kilometers separating these 2 mirrors. But in the early prototypes, it was just a few meters separating those mirrors. And a laser beam comes in through a beam splitter, and it enters through a hole in this mirror, and the light bounces back and forth many times. And we call this a delay line because the light is just delayed in getting back out by bouncing back and forth so many times. And similarly, the other arm, then the light comes back and it recombines at the beam splitter. And the key point is that if these mirrors have been pushed apart while that, if these mirrors have been pushed apart while that light was in there, and those have been pushed together, then the wave fronts of this light that's coming back to the beam splitter will have been delayed in arriving at the beam splitter with respect to the wave fronts of the light that's coming from the other arm. And that means there will be a change in the interference of the light. And that means that going toward a photodetector down here, we'll call this the output port going down, that going toward that photodetector, the intensity of the light rises and falls in proportion to the stretching and squeezing. So this is called interferometry, and with delay line arms. I looked at Ray's technical paper and I wondered what had happened to him. Had he gone crazy? I just did not seem to make sense to me. And we were within a few days of sending the manuscript of our textbook, Gravitation, that I was writing with John Wheeler, my thesis advisor, former thesis advisor, and Charlie Misner, to the publisher. And I put into that manuscript, just before it went off to the publisher, a brief description of this, and then an exercise for the student to show why this is not very promising. I ate crow, obviously, after that. Why did I think it wasn't very promising? Begin with 1 centimeter, divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that is being used. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the magnitude of the mirror motions that I thought would be the strongest mirror motions we would ever see for gravitational waves arriving at Earth if the mirrors were separated by a few kilometers separation. It was unbelievable to me that you could pull this off at that level, that you could see those tiny motions. And what was actually needed when you looked at what the technology was at the time was that the displacement noise for the mirrors moving back and forth due to various forces acting on them, not gravitational forces, including just thermal motions. The actual displacement noise, that even if you build a really good one of these interferometers in the laboratory, when you first turn it on, you need to beat that displacement noise down by a factor of 1,000,000. And then you need to increase the arm length to a few kilometers from a laboratory prototype. And 1,000,000, a factor of 1,000,000, I mean, that's just incredible. And then I had conversations on and off over a period of 3 years, 73 to 76, with Ray Weiss, with Vladimir Brzezinski, a brilliant experimental physicist in Moscow, Russia, whom I also highly respected. I studied Ray's paper, and I began to believe that maybe they had a shot at success. One November evening in 1976, I remember vividly, and this is Leah Halloran's recreation of this in a painting from our book. I wandered the streets of San Marino, just thinking about, should I propose to Caltech that we invest a huge effort in trying to help the experimenters pull this off? And my bottom line was yes. And so vignette number 3, 76 to 79, begins with, in 76, I proposed to create a Caltech research group in gravity wave detection and experimental gravity. I gave the proposal to Martin Schmidt. He was the astronomer who was accredited with discovering quasars. He was the chair of physics, math, and astronomy. We call it PMA at Caltech at the time. And he appointed a faculty committee, a very hard-nosed faculty committee of experts on the technologies that you would have to use in order to build these kinds of detectors. A faculty committee to study my proposal. That committee worked for 2 years. The first year, the committee worked hard, interviewing the experts in the field, doing their own calculations, talking to possible funding sources, and finally came to a conclusion, yes, we had a shot at success, but if we had the right kind of person to lead this, and then the second year was finding the right kind of person to lead this, and the choice was Ronald Drever, who was at the time in Glasgow, Scotland. And so the recommendation then of the committee was ratified by the PMA faculty, the Caltech administration, and it even went to the Board of Trustees of Caltech for their information, and they embraced it enthusiastically. Now, why Ronald Drever? Because this was going to be very, very hard, and he was exceedingly creative. And we felt that you had to have somebody who was really creative because it was going to be so hard, who could be inventive and invent things that would get you through various hurdles. So this is a list of names of things: Fabry-Perot arms, PDH locking, power recycling, signal recycling, that Ron, over the next several years or just before this, invented or co-invented. And they made significant improvements on Ray Weiss's original ideas. And so one of his ideas was that you do your gravity wave interferometer with what is called Fabry-Perot arms. Instead of having the light go through a hole in the mirror and then bounce back and forth many times, making many discrete spots on the mirrors and then come back to the hole, you send the light through the mirror's glass, and then you have a highly reflecting coating, a mirror coating on the inside. And the mirror, only a tiny bit of the light leaks in, but it resonates in here because it's an integral number of wavelengths of round-trip travel in between those two mirrors. So the light resonates and then it builds up. Basically, the mirror, this Fabry-Perot arm cavity, it sucks the light in that's coming in from the laser. And it builds up the light to what could be 100 or 1,000 times higher intensity than you had out there. And that gives you much better sensitivity. But it's very hard to make work technically. And that was the catch. And that was the reason that Ray Weiss was not enthusiastic about this. It was just so much harder technically than the technique that he was pursuing. Now, in order to get off the ground, it was clear this was going to be very difficult. NSF was not putting any money into this. NSF had given Ray Weiss $60,000  4 years earlier, and that's all he had gotten. MIT was giving Ray Weiss zero, absolutely zero, again, giving him zero encouragement. And so Caltech really had to go it alone. And so the president of Caltech committed $2 million of its own funds to get this effort off the ground. That inflates to $14 million today. And that's an incredible investment. At NSF, when they saw this investment from Caltech, they said, we better go look at this again. And they went in and they did their own study, came to a similar conclusion. They started funding both Caltech and MIT at a considerable level. And so we were off and running with federal support. Vignette number 4, the 1980s. In the 1980s, then, there were, it turns out, 4 research groups pursuing these kinds of gravity wave interferometers, prototypes in the laboratory. There was the MIT group with a 1.5 meter delay line prototype. This is Ray Weiss's group, about 15 graduate students and postdocs. And more importantly, in 80 to 83, Ray and his group did a feasibility study for interferometers with kilometer scale arms, which became then the foundation for our moving forward in the end of the 1980s, this study that he carried out. There was a group at the Max Planck Institute, a very different kind of a group. It was a group of 6 people. very small group, but they were all very mature, very accomplished physicists and engineers. They were all in they ranged from their 30s to their 60s, led by Heinz Billing. And they built, similarly, a delay line interferometer, a 3-meter and then a 30-meter delay line prototype, in order to see now how did things change as you started to make these arm lengths bigger. There was a group in Glasgow, Scotland, led by Ronald Drever, whom we then attracted to Caltech, and so he commuted back and forth, leading both the Glasgow and the Caltech groups for the next few years. But also by Jim Huff, who took over the leadership. And when LIGO discovered gravitational waves, Jim Huff was given a knighthood by Queen Elizabeth for his contribution to this. This is the level of excitement there was in the UK, because the Glasgow group made huge contributions to this in the end. And then it was Caltech group, Ron Drever and Stan Whitcomb, whom we brought from the University of Chicago as an assistant professor to work with Ron. And Stan became, in my view, along with Ray Weiss, the most important, the most influential of all the experimental physicists in the laboratory. He became, in some sense, the chief scientist of the LIGO project over the coming years. And they were working with a group of 18 grad students and postdocs. And by 1986, these four groups, partially competing with each other, partially interacting with each other, and shuttling postdocs back and forth between the groups, they reduced the mirror displacement noise by a factor of 1,000. And that meant they had another factor of 1,000 to go to get the factor of 1,000,000. So they were halfway there on this logarithmic scale. So that was quite an achievement. It was enough to make the world stand up and take notice and say, well, maybe, just maybe, they can pull this thing off. 1984, very late in this R&D work, we created the LIGO collaboration. It was created under the pressure from the National Science Foundation. Marcel Bardon was the head of physics. Richard Isaacson was the head of gravitational physics. And they knew that it was going to be impossible to get Congress to fund two independent efforts, and also that neither group by itself could possibly build up a strong enough effort to pull this off technically, so they demanded that there be a collaboration. There's this troika, this three-headed leadership of Ray Weiss, Ron Drever, and me at Caltech and MIT. And Ray and I said, of course, we're going to collaborate, and Ron Drever said no. Ron had a personality that made it basically impossible for him to work effectively unless he was in control of all aspects of the project he was working on. But there was no way he could be in control of this project because he was the most disorganized physicist I ever met. Certainly one of the most creative, no doubt, but also, and so this is the kind of thing you meet in the real world. You meet people who have ideal ways to contribute in some respects, and then there's some sort of a problem. Caltech, the head of PMA by then is Ed Stone, and he is enthusiastic about collaboration. At MIT, John Deutsch is the Dean of Science on his way to becoming the provost, and he's absolutely not interested at all. He thinks this is a waste of money, a waste of time, and Ray Weiss shouldn't be doing it, and MIT shouldn't be encouraging him. And so this, of course, was a prescription for dysfunction. Nevertheless, we accomplished a surprising amount between 84 and 86. And a few years later, in the early 1990s, MIT became enthusiastic when they had a new president, Chuck Vest, who really came around and turned the institution around. So vignette number 6, then, 1986. And this is the most important factor politically in getting us off the ground and moving forward. And so this is a story really worth paying attention to. There's a guy named Richard Garwin. He is politically the most influential physicist in Washington politically. He has the ear of Congress. He was a major contributor to the hydrogen bomb project. That was part of it. But he also was just a superb physicist, and he knew it, and they knew it. He wrote a letter to Marcel Bardon in February 1986, and this is a quote. I'm firmly of the view that we do not need right now to spend $40 million or $100 million on LIGO. That's what we were talking about. If there is such an interest, then I think it would be useful to have a 2-week summer study where people not involved in the experiment have a chance to contribute. So Marcel Bardon, the head of physics at NSF, a very wise guy, he together with help from Ray Weiss and Richard Isaacson at NSF, they organized a 1-week in-depth study of LIGO's plans and of the whole worldwide gravitational wave interferometer effort in November 1986. And it was a study by a committee of 8 experts in all the technologies required for success. Experts who, each of whom was extremely highly respected in the community and in Washington, including Garwin, who went into it, of course, saying this is a total waste of time, a total waste of money. After a week-long study, this committee, which is called a Blue Ribbon Committee, Blue Ribbon just refers to the enormous amount of influence that these people have had in Washington. They issued a report that said there's a high probability that LIGO will succeed. It will produce a giant leap in understanding of gravity and of astrophysical phenomena. The committee urges that LIGO's design be completed and its construction then be brought to NSF for consideration and hopefully for funding. And it is essential for LIGO to have 2 sites, at least 1,000 kilometers apart, even though Europe also plans on building big interferometers. Why? Because an international network, some in Europe and some in the US, will be crucial for extracting science from the observed waves. This, in fact, was a remarkably accurate blueprint for what actually happened. And when gravitational waves were ultimately discovered in 2015, I'm told that Dick Garwin beamed with pride that he had triggered this study, which had bought into this in such an influential way that it enabled things to go forward. That committee also said they had to get rid of this troika of leadership of Thorne, Drever, and Weiss. That's a crazy way to lead a project. And you get a single scientific project leader, and there must be a choice quickly of delay line versus Fabry-Perot. So in response to the Blue Ribbon report, Robbie Vogt, a Caltech professor, a PI on NASA space experiments, JPL's first chief scientist, and Caltech provost, he was appointed the director of LIGO. And he made the choice that we would go with the Fabry-Perot arms, even though the choice was not obvious because they still were extremely difficult to make work and they were not really working properly yet, even after about 8 years of effort. They were working, but not fully properly. But in retrospect, it was a very wise choice. 87 to 93, then under Robbie Vogt's leadership, Robbie hired 5 engineers. They completed LIGO's conceptual design and costed it. Robbie gave preliminary cost estimate of $180 million to NSF Director Eric Bloch. But there was a big misunderstanding. Bloch gave that $180 million to the Office of Management and Budget as a final total cost, and the die was cast. There was no way that that could be turned into anything but a final total cost. And to live with that cost, Robbie was forced into a very lean management structure and staff, very different than what we normally have for a big project. And that came back to bite us very badly after a couple of years. The LIGO team wrote a superb proposal for LIGO's final engineering, design, and construction. We submitted to NSF in November '89, and it sailed through tough reviews, was approved by the National Science Board in October 1990. In autumn of '91, after a battle with a powerful set of astronomers who went and lobbied Congress against us, they testified in Congress against us. They met with individual congressmen and staffers saying we should not be given a penny to move forward because this project was not going to succeed. I could hardly fault them. That had been my attitude at the beginning, when and they were not really experts on the technology. But in fact, we did get the funding from Congress. Why? Because of these blue ribbon type reviews. Committees were appointed that vouched for the project technically over and over again, and Robbie was very persuasive with Congress. The two LIGO sites were chosen, one in Hanford, Washington, the other in Livingston, Louisiana, with Caltech and MIT here and there. They could hardly have been farther apart from Caltech and MIT, but that didn't matter. They were very good sites, 3,000 kilometers apart. And Robbie's team developed detailed design and plans for the initial interferometers and brought facilities to the verge of beginning of construction. 93 to 94, the leaders of NSF demanded that as we moved into LIGO construction, Robbie had to change management from a lean management to a robust management, the kind of thing that is done in high-energy physics. Robbie, with his constrained budget, could not comply. He didn't have the money to manage it, and what he needed was an additional several tens of millions of dollars to do it in the conventional sort of way. Nor could he convince NSF to increase LIGO's construction budget, so after intense discussions, the Caltech president, Tom Everhart, replaced Robbie as LIGO PI by Barry Barish. That was a real, of course, blow, an ego blow to Robbie. And then Barry negotiated with NSF a budget increase of something like $30 million to pay for robust management plus a contingency. NSF had never done a big project like this before. Contingency is standard in big projects. It's basically money that's set aside to deal with unexpected things that come along that you hadn't planned for. And NSF had refused to give Robbie any money for contingency. But by then they understood that they had to do it, and so they gave it to Barry. Barry was highly qualified to do this. He'd been the leader of high-energy physics at Caltech. He'd been on the committee that recommended creating the Caltech Gravity-Wave group. And he'd been on many LIGO advisory committees. He appointed Robbie the leader of the initial LIGO interferometer group, the group that was designing and would then begin to construct components for the initial interferometers. Robbie, of course, his ego was badly bruised, but he understood that this was really important. In order to move forward smoothly, he needed to be part of this in a transition period. And so he held back his personal ego issues, and he accepted that. And for 2 years, he led the interferometer development effort, and Barry led the entire effort. But once things were going along really smoothly, then Robbie backed out, and he became an advisor to the president of the University of California on Los Alamos and other government labs that the University of California has. He moved in a completely different direction. And it was all then in Barry's hands. But I was very proud to see how they worked together to keep this thing going. 94 to 97, Barry reorganized LIGO. He more or less accepted Robbie's plans for the facilities, the vacuum systems and so forth that housed the interferometers, and for the initial interferometers after a detailed review. But Robbie had not had time or enough personnel to think much beyond the initial interferometers, and so Barry thought carefully. It was obvious to him that the advanced interferometers, if you did 2 generations, initial interferometers, and then you took them out and they didn't see any gravitational waves, and put in a second generation called advanced interferometers, that they would have to have a high probability of discovering gravitational waves, because there's no way Congress was going to continue funding for 3 generations at very large amounts of money with each generation. If you don't see it, if you tell Congress the first generation probably won't see anything, the second generation had damn well better see something. And so this had to be the philosophy. But many, many things could go wrong, so the advanced interferometers had to be highly complex. And let me illustrate the complexity in this way with photographs of what was ultimately built. This is LIGO at Hanford, Washington. This is the corner station in which the beam splitter and the corner mirrors hang, and those are vacuum pipes in which the beams go down to the end mirrors way long distance away, 4 kilometers away, and down to the lower left and lower right. So that's a photograph. And as I say, this is the corner station. That's what it looks like for the corner station in here. Sorry, come on. Barry has put a baseball player in here just to show you the size of a human compared to this. That's a vacuum tank in which the beam splitter hangs. This is a vacuum tank in which the corner mirrors hang, these two vacuum tanks. And then here's the vacuum pipe that holds the beams that are going out to the end mirrors. And so it's relatively simple. Here is the advanced interferometer. Those three chambers are way back here in the corner, and all of this other stuff is all the complexity that had to be put in order to pull off the advanced interferometer. It's enormously more complex. Another way to say it is that it turns out in the advanced interferometers there are 100,000 data channels. Now, it's hard to believe. 100,000? How can you possibly have that? Every component is instrumented and can be pinged and asked, what were you doing at the time that this purported gravity wave signal came along? And it will respond with details of what it was doing. Every component in there, and there are 100,000 components, is very, very complex instrument, plus the environment around it. And so of these 100,000 data channels, only about 1,000 are really detailed channels that are really interesting under normal circumstances, but you have the other 100,000 that can be pinged. The initial interferometers, as Barry saw, would reveal the pitfalls, and they would teach us how best to design the advanced ones. Barry then did a miraculous thing. He convinced NSF and Congress to fund the advanced interferometers well before the initial interferometers had reached their design sensitivity. If we had waited for the initial interferometers to reach their design sensitivity and they hadn't seen anything, and we were expecting them not to see anything, then you would have a long delay in order to design and build the components and install the advanced interferometers. It would have driven the costs way up. But to get the funding overlapping this way was unheard of. But it was something that Barry had the skill to make happen, and it was just incredible. Now, because of the complexity and also of the advanced interferometers, also data analysis, Barry planned for far more physicists and engineers than Robbie did. Robbie had about 40 scientists and engineers when Barry took over. Barry expanded to hundreds, and by 2015, about 1,000. And he divided them up into the LIGO laboratory, which is Caltech, MIT, Hanford, and Livingston, where the sites were. And the Caltech laboratory was in charge of the interferometers, building the interferometers and running them. And then the LIGO scientific collaboration was in charge of getting the science out and planning the science and interfacing the science to the interferometers. And this is, as of our first discovery of gravity waves in 2015, this is the LIGO scientific collaboration. There are 1,000 members at 82 institutions in 16 nations scattered over the entire world. It's included Glasgow, Scotland, Jim Huff's group, where he would get a knighthood from this, and the Max Planck group in Germany. But there was a separate group, an Italian-French group, that was moving forward with independently building a 3-kilometer interferometer near Pisa, Italy. This was called the Italian-French Virgo collaboration. So you now had two groups. You had LIGO moving forward with 2 sites. You had one site in Europe, the Virgo site. And I'll return to that in just a moment. Now I'm going to move back in time several years to 1992, when I'm thinking about the strongest sources of gravity waves that we would see and what that meant. And there was a general conclusion, agreement, that the strongest sources would be binary neutron stars, each one about 20 kilometers across and weighing about the mass of the sun, central densities of about 10 times the density of an atomic nucleus, that orbit around each other, collide, merge, and create electromagnetic waves as well as gravitational waves. And binary black holes, which is seen from the bulk here in an artist's conception from that era, they orbit around each other, collide, and merge, and become a single black hole. Now, the binary black holes, I had this view that the binary black holes typically will be 10 times heavier than the binary neutron stars, so we will see them 10 times farther into the universe. That meant that the volume over which those black holes are seen is 1,000 times greater than the volume over which you will see neutron stars. And I thought this is very likely to outweigh the rarity of black holes in the universe compared to neutron stars. And therefore, it seemed to be highly likely that the first things LIGO would see would be black hole binaries merging. And we would see many more of these than binary neutron stars. That was not a popular view. I was one of a handful of people who really thought that. But I began pushing very hard on this. And the key is that in order to understand the gravitational waves we saw from black hole mergers, we had to have theoretical waveforms that told us about the stretching and squeezing as time passes for black hole mergers in order to interpret the waves that we saw. And we didn't have those waveforms. We were very far from having those waveforms. And so that was a new track of research that had to be started. And we started in the vengeance in 1992, moving forward in parallel with the experimental track, the pushing of this. But there was a second aspect of my view in 1992. If nature is unkind, then the strongest waves will be so weak that quantum fluctuations of the mirror's positions will hide the waves. Let me be more precise. LIGO is instrumented in such a way that the interferometer is sensitive primarily just to the center of mass motions, the motions of the average position of all the atoms in a mirror. So each mirror behaves like a 40-kilogram particle. We have 4 40-kilogram particles with 4 mirrors. And we have to face the fact that just as an electron inside of an atom, you never know where it is. You only have a certain probability for where it is. Similarly, for our 40-kilogram particles, you only have a certain probability for where it is, and it's fluctuating around with this probability distribution. And those fluctuations will hide the gravitational waves if the waves are at the weaker end of the range in which I was expecting the waves. And so that was a big deal. And to deal with this quantum noise, we had to develop what is nowadays is called quantum precision measurement, or QPM technology. In technical terms, we had to invent a technology to circumvent the Heisenberg uncertainty principle. Quantum technology. And that was clear to me, very clear to me in 1992, but already one of my students had been working on ideas for this, and the foundations for this had been laid. And so the issue was we now needed to push hard on this quantum precision measurement technology as a new track 3. So we have three research efforts going on in parallel. You have the main gravity wave interferometer effort, you have the simulations of black hole binaries to understand the gravitational waves, and you have quantum precision measurement. You have quantum technology being invented. This is in parallel with inventing quantum computing, in parallel with inventing artificial intelligence. It's of a similar sort to that effort that's all going on at that time. As a preview, nature was kind. The strongest waves did not require quantum precision measurement technology, but we do need it today. We do have it today thanks to Track 3 effort, and it is playing a central role in getting science out of LIGO today and in the future. So a plan for the remaining few minutes of my lecture. I'm going to go through these quite quickly, obviously. I'm going to talk about Track 2, the binary black hole waveform computations, where the goal was to have mature enough computations of waveforms for the first gravity wave observations before gravity waves are discovered. So that became the goal of that track. Then I'll return to Track 1 and talk about the work that led up to the discovery of gravitational waves, and then I'll very briefly talk about Track 3, the quantum precision measurement technology, and LIGO today and in the future. Okay. Track 2, binary black hole waveform computations. The key to this, the key motivation is that there are 3 stages in the evolution of a binary black hole. You have the 2 black holes orbiting around each other as seen in our universe here. They in-spiral, and that in-spiral is described by what are called post-Newtonian equations. Those were in hand. We understood them quite well. They needed some additional work, but they are more or less in hand, and so that was not a big issue. Numerical relativity was the only way that we would be able to compute the waveforms from the merger period. And then once the black holes had merged, then you have the final black hole would vibrate and ring down like a bell. And that was controlled by the so-called Tucholsky equation, named after Saul Tucholsky, who had been a student of mine when he did this, developed this equation. And that was fully in hand. And so the key horribly difficult part was gravitational waves computed by solving Einstein's equations on a computer, numerical relativity, computer simulations. This effort had been underway since 1960, and it was not going anywhere very fast. And by the early 2000s, I became alarmed by the painfully slow progress on this. So I consulted with Saul Tucholsky, who had been leading this effort at Cornell already for about 15 years. He'd done the key thing on the black hole ring down. He'd been leading the numerical relativity effort. He was, in my book, the strongest of the computational physicists doing this. And I said, what kind of effort will ensure that we have robust binary black hole simulations before advanced LIGO needs them? And our conclusion after looking at this quite deeply was that Cornell-Caltech collaboration of about 30 outstanding numerical relativists. Why so many? Because of the great complexity of the problems that had to be solved. It was like advanced LIGO, but on a theoretical computational science end. Not as bad as advanced LIGO, but pretty darn bad. And this is what Dan was talking about, that he was seeing the tail end of this when he was at Cornell, and they were just in the process of completing that effort. Caltech provided us with seed funding and helped us get long-term funding of $1 million a year from the Sherman Fairchild Foundation to augment NSF and NASA funds, and we built a collaboration of 30 computational scientists at Caltech and Cornell called the SXS Collaboration for Simulate Extreme Space-Times. In spring of 2005, one of our postdocs, Franz Pretorius, achieved the first simulation of the in-spiral, just one orbit, and then the final in-spiral and the merger of identical non-spinning black holes. And he did it single-handedly by combining a few new ideas of his own with techniques of others for overcoming various pitfalls. He got a professorship at Princeton University out of this, a breakthrough. And this was his first gravitational waveform for the merger, and it was very simple. It was much simpler than I expected. This is the beginning of where the waveform is believable. You only look at the solid line. The other lines are something irrelevant. This is where the horizons touch halfway through here, and that's the ring down afterwards. And surprisingly simple, and it took us a while to understand why it was so simple. And there's deep geometric dynamics of warp space-time behind that. But that was by far too little for us to move forward with advanced LIGO and be able to do the data analysis. We needed simulations of a wide range of black hole masses and black hole spins. And so the SXS team under Saul Tucholsky's leadership, with Larry Kidder, Harold Pfeiffer, and Mark Schill being the primary authors, wrote a computer code that reached maturation in 2013. And by 2013, they were able to simulate binary black holes with mass ratios up to 8-to-1. The heavy one is 8 times heavier than the light one. Spins up to 90% of the maximum allowed spin by the laws of physics in near circular orbits. And here are a bunch of the waveforms that they generated. They had a catalog of 171 simulations, 140 more were underway. And this was adequate for LIGO's first detections. 2013, the first signal came in 2015, sort of almost just under the wire. So back to track one, the construction, installation, and commissioning and operation of the initial LIGO interferometers went remarkably well. It followed Barry's plan, except for a several-year delay due to Washington politics. There was politics of no new starts of any projects in the George W. Bush administration, affecting not just us, but all other projects at NSF and NASA. In 2006, the world's high-energy physics community begged Barry to resign as LIGO director and go lead a design study for an international linear collider. With LIGO in good shape, Barry did leave, and J. Marks from Berkeley came and succeeded him. But Barry stayed on 20% time, but not in a leadership role. And under Marks, the LIGO-Virgo collaboration was made, an agreement that LIGO and Virgo, that was the other group that was building the detectors near Pisa, Italy, that we would analyze our data together. We basically would form a collaboration. So there was one international network of gravity wave detectors, 2 in the United States and 1 in Italy. Because of the delay, we had a little extra time, and so the initial LIGO interferometers were pushed harder, and they went to 2 times better than design sensitivity, at least in at frequencies above about 150 hertz. So they could see 8 times farther volume in the universe, and so it was considerably better a search carried out that way, but nothing seen. In 2010, there was a smooth transition to installing the advanced LIGO interferometers. LIGO then, leadership went to David Wrightsey beginning in 2011, a smooth transition from J. Marks. And on September 14, 2015, the advanced LIGO detectors were being tuned in preparation for their first gravity wave search to begin on September 18. And an apparent gravity wave signal arrived. David Wrightsey declared that the first search had begun. They froze the detectors in the configuration they were in and continued searching. This was premature by a few days from what had been expected. This is the story of that first signal 1.3 billion years ago in a galaxy far, far away. 2 black holes orbit around each other. This is what they would have looked like to your eyes if you had been there. This is gravitational lensing of starlight and stardust from the sources that are beyond those black holes. And as you're seeing the shadows of the black hole horizons then in front of the stars. The black holes emitted gravitational waves, spiraled together, and produced a burst of gravitational waves that traveled out of the galaxy in which the black holes lived into the great reaches of intergalactic space for 1.4 billion years. They traveled across the great reaches of intergalactic space until 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. This burst of gravitational waves reached the outer edges of our Milky Way galaxy. On 14 September 2015, they touched down on the Earth at the tip of the Antarctic Peninsula, as best we can estimate it. They traveled up through the Earth unscathed, emerged from the Earth at the Livingston, Louisiana gravity wave detector, LIGO interferometer. And 1,000th of a second later, 7 milliseconds later, they emerged at Hanford, Washington. They wiggled the arms of the interferometers. The interferometers recorded the signal. And the LIGO-Virgo collaboration now, the Virgo group participating in this, analyzed the data for 5 months to be absolutely sure this is really what it looked like it was. And then announced the result, which made front page reporting in all the big major newspapers around the world and many of the minor newspapers. The New York Times, with faint chirp, scientists prove Einstein correct. And what did we see? By comparing the SXS numerical relativity simulations for, you adjust the masses and spins of the black holes until you get a good agreement with the cleaned up gravity wave signal in gray. They concluded it was the inspiral and merger and ring down of a binary black hole. That the initial black holes weighed 29 and 36 solar masses, so 65 times the mass of the sun. The final black hole weighed 62 times the mass of the sun, and 3 solar masses went into gravitational waves, and it all happened so fast that the power output, the energy per unit time during the merger, was 50 times larger than the luminosity of all the stars in the universe put together. 50 universe luminosities in that sense, in gravity waves. no electromagnetic waves whatsoever, and at a distance of 1.3 billion light years. This is what it looked like as seen from the bulk, from a SXS simulation. You see the funnels in the bulk that represent the black holes. You see the color coding showing the slowing of time. Where it's black, that's inside the horizon. And at the moment of collision, there's a huge splash in the shape of space, and then an oscillation in the shape of space in the rate of flow of time, and the gravitational wave burst goes traveling out. 2017, 2 years later, the Virgo detector is now online. It was not online previously. It's now beginning to work pretty well. Virgo is now by then a collaboration of 19 laboratories, 250 plus scientists in France, Italy, Netherlands, Poland, and Hungary. This is a picture of the corner station. And, And a binary black hole merger occurs, and now having 3 interferometers, so you could triangulate in 2 dimensions on the Earth from the delay time and arrival of a signal. Here is the error bar on where on the sky. This is basically a map of the sky. This is where the signal was. All of the previous signals, you couldn't localize them in 3 dimensions. For the first time you could. And then a matter of just a few days after that comes the gravitational waves from the collision of 2 neutron stars. And with the 3 detectors online, you could triangulate and see where the gravitational waves are coming from. You have a fireball that generates all forms of electromagnetic waves that astronomers are capable of seeing. It's called a kilonova. And just after the gravitational waves come in, 1.7 seconds later, with the gravitational waves from this little error box on the sky, the gamma ray burst comes from that region on the sky. Then over the next few hours and then days, there is X-rays, ultraviolet, optical, infrared, and radio, all coming from a galaxy that's down here at that location. And this is the world's first multi-messenger astronomy event. And from the observational data, they concluded that a large fraction of all the gold and platinum in the universe is created in this way. Quantum precision measurement, I'll just say that QPM was invented in the 60s, conceptually by my student Carlton Caves. Technology was to do it was invented by Jeff Kimball down the hall from us. The technology was perfected and made robust by the LIGO team in 95 to 2020. And LIGO today is in the domain where mirror quantum noise can hide the gravity waves, but QPM is fully operational in LIGO, and the noise is being hidden. It's being controlled by quantum technology. And this is enabling LIGO today to see several black hole collisions each week. LIGO has now seen about 300 black hole collisions. It's been exploring the laws that govern black holes and the properties and populations of black holes in our universe. It has seen several collisions of neutron stars, but only one that was close enough to see the electromagnetic waves. Seen several black holes swallowing neutron stars, but none of them close enough to see the electromagnetic waves yet. It is exploring the warp side of our universe with gravitational waves. This is truly the beginning of gravitational wave astronomy, and I think I should hold it there and just tell you that the future is extremely bright. The discoveries that have been announced just in the last few weeks are quite phenomenal. For example, there was a source that had a huge signal-to-noise ratio of 80 that was just the right kind of source to test Stephen Hawking's theorem that says that the surface area of the final black hole in a black hole merger must be larger than the sum of the surface areas of the initial black holes. And in fact, the test was carried out with a conclusion, with a confidence of about 1 part in a million, that the probability that this was violated, his law was violated, was 1 part in a million of a violation of Hawking's law. So precision tests of the fundamental laws that govern black holes are being done. And I think over the coming years, there are going to be huge surprises, particularly, I think, in the coming years when we are studying the gravitational waves from the birth of the universe. That's a whole other story. Let me stop at that we can have some questions.
Wow. Thank you so much. I feel like so often science is presented as the work of lone geniuses, and certainly that is an aspect of it, but it's so nice to see the journey of so many people, the human journey of trying to do these difficult things together.
And bringing together everything from the political side of things as well. Let me just say that when the discovery was announced, both the Republicans and the Democrats in Congress beamed with pride that they had supported this rather firmly through the transition from initial LIGO to advanced LIGO. Both the Republicans and the Democrats had backed this to the hilt. You don't see that happening much today, but in that era, we had that kind of backing, and they really, truly took pride in this.
We have a few minutes for questions. You can scan this QR code to enter your questions. McKenna McMurray, a senior in engineering, one of the people on the Nelson Series committee that helped put this together, will be reading them out. So maybe she can start us off with the first question, and you can add them there as you want.
Here now. I had a knee replacement operation not very long ago, and I'm not great on my feet. So.
Oh, no worries.
Okay. Okay, please.
Okay, so for our first question, our series is titled Doing the Impossible. Clearly this comes pretty close to doing exactly that done over the span of several decades. Could you comment on the importance and value of striving to do hard things and break difficult barriers? And how do you keep yourself and everyone around you going when things get hard over multiple decades?
I didn't get the full question. Say this more
slowly. I'll start with the first part. The first part is, could you comment on the importance and value of striving to do hard things and break difficult barriers?
I think the key issue is you strive to do hard things if there are huge potential payoffs. And I think we tend to shy away from really hard things. And this was an example where the world was shying away. If Caltech had not bought into it when Caltech did, it would probably have been a long time before it ever happened. LIGO is a case lesson, and a case lesson that I think people in Congress, as well as in the scientific community, have paid a lot of attention to since its success. It really is a lesson of, and there's an issue of whether or not, if this were happening today, whether or not LIGO would have happened. I think the answer is probably not, but we're much more risk averse today than we were then.
The next question from someone was, how do you feel when the first signal was detected?
So I'm going to describe my feeling, Ray Weiss's feeling, and the younger generation's feeling. My feeling was a sense of, once we were sure it was a real signal, and that took, as I indicated, several months. Once we were sure it was a real signal, I simply felt profound satisfaction that that I personally had made some very wise choices along the way, including the choices to push hard on the numerical relativity simulations, the choice to push the quantum precision measurement, which it turned out we didn't need then, but it was clear we were going to need shortly. But there were a large number of other choices. Just a sense of profound satisfaction that by looking very, very carefully at what could go wrong and what was most important in avoiding the things that could go wrong, that we as a team had made wise choices. Ray Weiss's had this feeling of guilt that he had convinced a huge number of young people to get into this field, and they'd not seen any gravity waves yet. And that we had spent $1 billion of taxpayer money, and they hadn't seen any gravity waves yet. So he had a sense of profound relief, which is an emotional reaction. But the younger generation of people who really were central to pulling it off they just felt euphoria.
The next question is from Zoe, and she's asking, what about LIGO do you think brought people of different politics together, and how might scientists and other folks working on big projects encourage and replicate that kind of universal excitement?
I think that I said it in the talk, and let me say, I really came to believe this as I look back on the LIGO history that we've been doing for the past 5 years. The central thing that brought people together was these intense reviews by hard-nosed committees of experts on the technology, saying time and time again, okay, here are a few things you should be paying more attention to, but by and large, you're on track. You should keep going forward. And that just outweighed the skepticism that we were meeting in some quarters. And I think it weighed heavily with Congress. It weighed heavily with the leaders of NSF. Leaders of NSF came to back this, beginning with Eric Bloch, who was the guy who drove us through his misstep on calling a preliminary budget the final budget. He got us into some trouble, but he, as a LIGO director, he was a LIGO director who bought in enthusiastically, and every LIGO director thereafter bought in enthusiastically. And I've interviewed them all that are still alive, and their level of enthusiasm was quite remarkable. And I think it came from these blue ribbon reviews.
Our next question is, why did you fall in love with general relativity? Was it naturally appealing to you, or did someone or some event inspire your curiosity?
I think it's, who wouldn't love the idea that space and time are warped? I was a kid, I was 13 years old, I fall in love with astronomy. Then I learned from this book by George Gamow that there are laws of physics that control the universe, and that among the laws of physics are these, where gravity arises from a curvature of space-time or warping of space-time. And just that whole idea was just so neat that I wanted to understand it. And I didn't really understand it, and I couldn't find a textbook that really explained it in a way that I could understand. And so I went to Princeton because it was obvious that the best person to learn to understand it from was John Wheeler. But,
So I think we have time for one more question. I know that lots of people want to get their books signed afterwards.
So for our last question, someone asked, can you comment on the importance of science communication in your work? Do you think a liberal arts education like the one MUD and the Claremonts offer make better scientists?
I think liberal arts education has enormous value for ever so many reasons, but I think liberal arts education is very important for scientists, yes. And Caltech, I was always a strong advocate that we educate our students broadly, and that they get, in effect, the liberal arts kind of education that you get at Harvey Mudd. And that was our goal in my years of teaching there. Science communication, I think, is of very high importance for a variety of reasons. Partly, in my area, it's an ethical thing. We depend on the children of the general public to come in and study STEM science and become scientists, to do the things that we want to see done, to be the next generation that makes LIGO succeed. And we depend on the taxpayer money for a project like this. And it's in our self-interest to try to excite the general public about the things that we do for that reason. But it's also an ethical thing that we really, and this is something I learned from John Wheeler, who believed it very deeply, that we feed we have an obligation to give back, and to give back by inspiring the general public about what we do. My main reason for, besides having fun for working on the movie Interstellar, was how else could I reach 100 million people and inspire them about the power and beauty of science. And so I think some of us should be spending a huge amounts of time on outreach. Others don't necessarily have to, but the community as a whole needs to do a much better job than we have been doing. And the fact that there is so much misunderstanding of science in the general public, I think, is a warning that we've not been doing an adequate job.
Wonderful. Well, just wanted to thank everybody for coming. I hope you enjoyed this as much as I did. Professor Thorne won't be taking questions here at the front. He's actually very graciously agreed to sit out in the lobby and sign any books that you might have. But let's finish by giving Professor Kip Thorne a great round of applause.